Okay, hi everybody. So today we're going to go ahead and go over section 4.2 of linear algebra, which is subspaces. In section 4.1, we started dealing with vector spaces, and we went through the 10 different axioms that you needed to have in order for it to become a vector space. This is essentially the same idea, but now it's called a subspace. Um, and so the idea here is that it is a vector space, but it's contained in the original vector space. So you see what we mean here, okay? So here's what we have. So a subset W, let's make sure you guys can see that. Here you go. Okay, so we have a subset W of a vector space V is called a subspace of V if W itself is a vector space under addition and scalar multiplication. Defined on V. Okay, so as long as it's defined the same way and it's contained in that, it is a subspace. Okay, now if you think about this, there's certain, so to go through and show that's a vector space, you actually have to go through and show that it abides by the 10 different axioms there. But you actually don't need to do the 10 total axioms because there's certain of those axioms that actually inherited by being a vector space. For example, commutative property, associative property. If it's commutative or associative in the original vector space, it's still going to be commutative or associative in the subspace. So there's certain things that are inherited, but some of things are not inherited. Okay. Um, so there are certain axioms that are not inherited from the vector space V. Okay, so what would these be? Okay, one, closure under addition. Okay, so axiom one, closure under addition. Okay, say we take a space and we confine it, it's still possible to take two elements in that, add it together, and get an element outside of it. So it's not necessarily closed by making it a smaller space. Okay. In turn, you could also say axiom six. I'm going to kind of jump around a little bit because I'm going to kind of go with the ones that are together. So axiom six is closure then under scalar multiplication. Okay, once again, just because it's closed under scalar multiplication from before doesn't mean that once you constrict it that it's still closed under scalar multiplication. Okay, axioms, going backwards a little bit, axiom four, the existence of a zero element, zero vector in W. Okay, so we don't know that that exists. And the last one, which I'll have to go over here, is going to be axiom five. And axiom five was the existence of a negative in W. Okay, so the existence of a negative element in W. Okay, so those are the four different axioms that are not necessarily inherited, from the original vector space. Okay? Now, what's pretty cool about this, though, is if you look at this next theorem, we can actually ignore axiom 4 and axiom 5. Okay? So about theorem 4.2.1, a little bit closer here. So I have here, if W is a set of one or more vectors in a vector space V, then W is a subspace of V if and only if the following hold. So A, if U and V are vectors in W, then U plus V is in W. And if K is any scalar and U is any vector in W, then KU is in W. This is an if and only if statement. So technically speaking, to prove it, we have to go both directions. We are going to do both directions here. Okay, so we're going to tell the proof. I know I tell my students all the time that we're telling its story. This actually has a story to it, but I'm going to write proof. Okay, so we're going to go in the right direction first. Okay, so what do we assume? We assume everything before the if and only if statement. So W is going to be a set of one or more vectors in a vector space. So V is a vector space. Then W is a subspace of V if and only if. So we need to show that it is if and only if these things are true. Okay, so if W is a subspace of V, then all the axioms hold because it is a subspace. Okay, then all the axioms hold, and we're done, right? Because we only need to show that it was closed under scalar multiplication and addition. So we're done. Okay, so let's go the other way. Okay, so now what are we assuming? Now we're going to assume that it is closed, that if U and V are vectors in there, then U plus V is in there. And then also if K is any scalar, then KU is also in there. Okay, so that's what we're trying to show. Okay, so we're going to assume here that A and B hold. We're assuming that those are true. Okay, so these are axioms 1 and 6. And we also know that axioms, all the rest of, well, not all the rest of them, but 2, 3, 7, 8, 9, and 10 are inherited from V. Okay, those are like the associative, the commutative, and so on. Okay, so all we need to do is show that axioms 4 and 5 work in order for it to actually be a vector space. Okay, so we're going to let U be any vector in W. Okay, we're going to let it be any vector in W. Okay, so it follows that KU is also in W by condition B. Okay, we know that that's true. In particular, we have 0 times U because it's true for any scalar. And 0 times U is 0, which is the 0 vector. Okay, so I basically showed that it had the 0 element. And we also know that -1 times U is equal to -U is also in W. And that's the -1. So axioms 4 and 5 hold. So W is a subspace of V. And we're done. okay, because we only needed to show those two things. Okay, definition 4.2.2, there are some special subspaces that we always need to be aware of, okay? So zero subspace. If V is any vector space, and if W is equal to 0, and that's the 0 vector, is the subset of V that consists of the 0 vector only. So that's the only thing that has in there is only 0. Then W is closed under addition and scalar multiplication, since 0 plus 0 is equal to 0, and K 0 is equal to 0 for any scalar. We call 0 the 0. We call this a 0 subspace of V. Okay, so pretty simple. There's nothing more to it than that. I just need to go through and define what the 0 subspace is. Okay. Okay, lines through the origin are subspaces of R2 and R3, okay? What do I mean by that? So if W is a line through the origin of either R2 or R3, then adding two vectors on the line W, or multiplying a vector on the line W by a scalar produces another vector on the line W. Okay, so therefore it's closed under scalar multiplication and addition, and therefore it is a subspace. Now, what does that mean? Why exactly does that work? Okay, well, if you think about this, and I'm only going to do this for a line. Okay, so you have a line that goes to the origin that looks something like this, and this is the line W. If you have a vector that lies on this, and you add it to another vector, well, how do you add vectors together, tail to tip or tip to tail? So you go hip here. And so if you took that vector plus this vector, it's going to give you the whole entire vector, which still lays on that line. Okay, same thing, it could be said for a vector when you multiply by a scalar. If you take that vector and you multiply by a scalar, it's just going to be a vector that's either stretched out like this or even possibly shrunk, but it's still going to remain on that line. Now, why is it so important that it goes to the origin? That's because so it has a 0 element in it. Okay? Okay, so next page. So example 4.2.2. Okay. So if U and V are vectors in the plane W through the origin of R3, then it is evident geometrically that U plus V and KU lie on the same plane W for any scalar K. Thus, W is closed under addition and scalar multiplication. Okay, so it's kind of the same argument that we had from before. What I'm going to do is we're going to talk about what are some subspaces then. Okay, so here's what we have. Okay, so the following table gives a list of subspaces on R2 and on R3 that we have so far. Okay, we'll actually go on to show later that these are the only ones that are subspaces. Okay, so subspaces of R2. Okay, so what are the ones that we talked about already? Okay, we talked about the 0 subspace. Okay, so that's a subspace there. Okay, we also talked about lines through the origin. And we actually talked about one more, although indirectly, R2. R2 is a subspace of itself, okay, which is kind of interesting. Okay, and then over here, we're going to have subspaces of R3. Okay, once again, 0. The 0 vector space is a subspace. We have lines through the origin. We have planes through the origin. And then once again, we have R3, which is the subspace of itself. Okay? Okay. What about matrices? An n by n matrix. Okay? So here's what we know. We know that from theorem 1.7.2, and I leave that to you to go back and look that up what that is, that the sum of two symmetric n by n matrices is also symmetric. So we're dealing with closure, okay? When you add two symmetric matrices together, you get another symmetric matrix, okay? And I think it should be pretty clear when you multiply it by a constant, just given a multiplication, it will still be symmetrical, okay? Thus, the set of symmetric n by n matrices is closed under addition and scalar multiplication. Okay. To make an extension of this, we also know that upper triangular matrices, lower triangular matrices, and diagonal matrices will also abide by the same rules. Okay. Example 2.4.2. Determine the set of invertible n by n matrices is the subspace of m and n. So in other words, if you took two invertible matrices and you added it together, would you get another invertible matrix? And if you took an invertible matrix and you multiply by scalar, would you get something else that is also invertible? If you want to think this out for a minute, just go ahead and pause me for a moment. But it turns out that this is not the case. And that's because I can consider, so we're going to consider here two invertible matrices. And I have U, which is going to be the matrix 1, 2, 2, 5. And then I have the matrix V, which is actually just its negation, -2, -1, -2, -2, -5. You can go through and check that these two are invertible simply by taking the determinant of each. I'll do this one. 5 minus 4 gives you 1, so it's not 0, so it is invertible. So this is invertible. This is also an invertible matrix. But you notice if I took U plus V, that gives me the matrix 0, 0, 0, 0, which is a 0 matrix, and that is not invertible. So it is not closed under addition, and therefore the set of invertible n by n matrices is not a subspace. Okay? Okay, then we just have a couple of different definitions here. Okay, and these are important to know as we work forward with these because they'll come up quite a bit. Okay, so it says in calculus, we know that the sum of continuous functions is continuous and a constant times a continuous function is continuous. So deal with the set of continuous functions. So then the set of continuous functions on the interval from -infinity to infinity is a subspace of f of -infinity to infinity. So f of a -infinity to infinity is the set of all functions that are defined on that interval. Okay, we denote this as a subspace of c from -infinity to infinity. Okay, we can take this a step further. Okay, in calculus, we know that the sum of two continuously differentiable functions is continuously differentiable, right? If you take two things that are continuously differentiable and you add them together, you're going to get something else that's continuously differentiable. Thus, the functions that are continuously differentiable on the interval from -infinity to infinity form a subspace on f of negative infinity to infinity. Okay, we denote this subspace as C1. Okay, so you can take the derivative one time. Okay, furthermore, the set of functions with m continuous derivatives from negative infinity to infinity is also a subspace of f of negative infinity to infinity. And we denote this as Cm of for negative infinity to infinity. So we're able to take the derivative m times on this set. Okay, if we have the set of functions that is continuously differentiable on negative infinity to infinity, so that would be a function like e to the x or sine of x, then this is also constitutes a subspace of f of negative infinity to infinity, and we denote this as c of infinity from negative infinity to infinity. Okay, so some big definitions there. Okay, next page, example 4.2.5. Okay, so now we're going to deal with some other things, okay, that are subspaces here. Okay, recall that a polynomial is a function that can be expressed as a p of x is equal to a naught plus a1x plus a2x squared all the way up to an xn. Okay, and this is where a naught, a1, all the way up to an are constants. Okay, so that's what a polynomial is. That's how you can define it. That's what a polynomial actually looks like. Okay, you can tell that if you take a polynomial and you add it to a polynomial, you're going to get back another polynomial. And if you take a polynomial times a constant, you're going to get back another polynomial. Okay, so it is evident that the set of all polynomials is closed under both addition and scalar multiplication. Thus, the set W of all polynomials is a subspace of f of negative infinity to infinity. And we denote this as p of infinity. Okay, so the set of polynomials is a subspace, which is kind of curious because now we're kind of viewing polynomials as vectors, right? It's an element of that set. The same result holds for polynomials of the set of polynomials where all the polynomials in the set are of degree less than or equal to n. Okay, and we denote this as Pn. Okay, intersection of subspaces. Would the intersection of subspaces constitute a subspace of itself? And the answer does turn out to be yes. Okay, so if we have W1, which is a subspace, W2 all the way to WR are subspaces of a vector space V, then the intersection of these subspaces is also a subspace on V. Okay, and once again, we are going to tell its story. Okay, so proof. Okay, so we're going to let W be the intersection of W1, W2, all the way up to WR. Okay, now what do we have to show? In order to show that it's a subspace, we have to show that it's closed under addition and that it's closed under scalar multiplication. But before we even do that, we have to make sure that there's something in there, right? Because if there's nothing in there, then it kind of is like a silly question, right? Of course it's going to be closed under addition. Of course, it's going to be closed under scalar multiplication if there's nothing in there. So we first have to make sure that there's something in there. So will there be something in there? And the answer is yes, because if you take this subspace, all these subspaces, and you find the intersection of them, well, 0 is going to be in each one of those because 0 is an element of every single subspace. So 0 must be an element of the intersection of those subspaces as well. Okay, so this set here is non-empty because 0 is in W. Okay, we know that that's true. Okay, so all we need to do is show that it's closed under scalar multiplication, scalar addition. Okay, so we're going to show it closed under addition first. Okay, so we're going to let U and V be vectors in W. What we want to do is we want to show when we take U plus V, it's going to end up back in W. Okay. Now, since W is the intersection of W1, W2, all the way up to WR, then U and V also lie in each of these subspaces, right? If it falls in W, and W is the intersection of all that, by definition, that means that U and V have to be in each one of those sets. Okay? So, since each one of these sets is closed under addition, then they all contain the vector U plus V. And therefore, U plus V is in W. And therefore, W is closed under addition. Wait a minute, I didn't leave room for scalar multiplication. That's because that is left as an exercise to the reader. Ha ha ha. Okay, linear combinations. What is a linear combination? Now this goes way back. If you guys have been around me long enough, you know what a linear combination is. You should know what a linear combination is. But we're going to go ahead and define this so we can move forward with this. Okay, so if W is a vector in a vector space V, then W is said to be a linear combination of the vectors V1, V2, all the way up to VR, which all lie in V. Sorry, I'm cutting you off there. If it can be expressed in the form So W is equal to K1 V1 plus K2 V2 plus all the way up to KR VR. So the key here is we have some vector W that we're actually able to construct using these other vectors. So the other vectors, V1, V2, V3, if we can take and multiply some constant by each one of those, add them together, and have equal to W, it's called a linear combination, okay? And so this is where K1, K2, all the way up to KR are simply scalars. Okay, and these are obviously called coefficients. Uh-oh, my video froze. There we go. Okay, I think we're back. I'm not sure what that's going to look like, but I know I froze for a moment. So I don't really want to stop and go back and record this. I'm just going to continue along. Okay? Okay, so the next theorem, 4.2.3. Okay, so if S is equal to, I should write this. This should have vector notation or set notation. So if S is equal to W1, WT, or W2 all the way to WR is a non-empty set of vectors in a vector space, then A, the set W of all possible linear combinations in S is a subspace of V. Okay, so let's dissect that a minute. So we have S, which is the set of all of W1 through WR. It's a set of vectors in a vector space V. So you take all the vectors in a vector space V, and you go ahead and put them in here, okay? Now, if you take any linear combination of these elements, W1, W2, all the way up to WR, and you take that set and call that set W, then that will be a subspace of V. Okay, so for example, W1, that is a linear combination of that set. I know it's silly. Or 2W1 plus 3W2, that is a linear combination of those. You take all the possibilities there and put them together, it will make a subspace of V. Okay, okay, B, the W in part A is the smallest subspace of V that contains all the vectors in S in the sense that any other subspace that contains those vectors contains W. Okay, so not only does it form a subspace, but it forms the smallest subspace out there. Okay. Okay. So we're going to prove this if we have room here. We'll see. Okay. We're actually only going to go through and prove A here, though. Okay. So proof. Okay. A only. And only show that it's closed under addition as well. Okay, that's all we're going to show. Okay, so we're going to let W be the set of all possible linear combinations of the vector of the vectors in S. Okay, so we're going to take them all. Okay, so we just have to show that it's closed under scalar multiplication and addition. But once again, we're only going to do addition. So we're going to let U be equal to C1W1 plus C2W2 plus all the way up to CRWR. Okay, so that's just a linear combination of all those W's there. And V be equal to K1 W1 plus K2 W2 all the way up to KR WR. Okay, so let's take a look at what do we get when we get U plus V. So U plus V, I'm just going to add these two vectors together. But you notice I have C1 W1 plus K1 W1. So I can factor out the W1. So I end up with C1 plus K1 W1 plus C2 plus K2 W2 all the way up to CR plus KR WR. And you can see now that it's closed under addition, right? We took an element here, U, an element here, V, which both belong in that set. We added them together, and we could rewrite it like this, where you now have a constant. This is just a scalar. C1 plus K1 is just a scalar times W1. So each one of these, let's go ahead, it's in that form. And so thus, W is closed under addition. Okay? It's pretty simple. Okay, I'm going to leave the rest of it for you to go ahead and decide what that's going to be. Okay. Next, definition 4.2.6, span of a vector space. So this is a very important term, and this will come up. We'll talk about what is the span of this, or does this set span another space? Okay, so the subspace of a vector space V that is formed from all possible linear combinations of the vectors in a non-empty set S is called the span of S. Okay, and we say that the vectors in S span that subspace. Okay, so that is if S is the set W1, W2, all the way up to WR, then we denote the span of S by, and simply, span of W1, W2, up to WR is equal to the span of S. Now, why does this matter? Like, why is this important? Basically, what we're doing here is we're going back and we're going to simplify a space as much as possible. We're going to say, what are its initial elements? What are its essential elements that you can take the system and you can build the whole entire system off of this small set, off this subspace. For example, if you consider the the Cartesian plane, the xy plane. Okay, that is spanned by two vectors, I and j. I the vector 1, 0, and j the vector 0, 1. You can take any linear combination of those, and any single point that's on the Cartesian plane, you can construct off of a combination of I and j. Okay, so it's like the power, we're breaking it down to its essential core, like what are its essential elements. Okay, so example 4.2.6. Okay, so we're going to recall that the standard unit vectors in Rn are, and remember we called them E, remember, because we went more than 3, it was IJK. When we went to the 4th dimension, then we just start using these E's. So this is going to be the vector 1, 0, 0, all the way out. E2 is going to be the vector 0, 1, 0, all the way out. And then En is going to be the vector 0, 0, all the way out to 1 there. Okay? Where, once again, each one of these has n elements inside of this. Okay? So these vectors span Rn, since every vector of the form v is equal to v1, v2, all the way to vn in Rn can be expressed as v is equal to v1 e1 plus v2 e2 plus v3 e3 all the way out to vn en. Okay, so every single vector that's in that space can be constructed off of those standard unit vectors. Okay. For example, if we're dealing with R3, okay, so R3 we have the vectors I, which is the vector 1, 0, 0, j, which is the vector 0, 1, 0, and k, which is the vector 0, 0, 1. And if I simply took some vector in that 3 space, say A, B, C, I could make V equal to AI plus BJ plus CK. Okay, so I'm able to construct it simply based off of those 3 vectors and those 3 vectors alone. Okay. Okay, next page. You got 2 pages left. Okay, see how long this takes us. Okay, so spanning the set for Pn. Okay, so now we want to create a set that will span P of n. P of n is a set of all polynomials of degree length n or less. Okay, so the polynomials one x, x squared, all the way up to xn span the vector space Pn since each polynomial P in Pn can be written as P is equal to A naught plus A1x plus A2x squared plus all the way up to AN xn. Okay? So what we know is that P of n then is the span of the set 1, x, x squared, all the way up to xn. Okay, so you take the span of that, you get the set of all polynomials of degree n or less. Okay, example 4.2.8. Consider the vectors u, which is 1, 2, negative 1, v, which is 6, 4, 2, and they should both in R3. I want to show that w, which is the vector 9, 2, 7, is a linear combination of u and v, and that W prime, which is the vector 4, -1, 8, is not a linear combination of U and V. Okay, so if it is a linear combination of U and V, so then I know that I can rewrite 9, 2, 7 as some constant k times the vector 1, 2, -1 plus some other constant I'll call L times the vector of 6, 4, 2. Now I just have to be a little bit clever and figure out what this is going to be. So I'm going to go and match up the parts. So I have 9 is equal to k plus 6L. I also have 2 is equal to 2k plus 4L. And I also have 7 is going to be equal to -k plus 2L. Okay, just playing around here a little bit. It's pretty easy to see that if L is equal to 2 and K is equal to -3, that this will work. Okay, so you go up here. I'm going to take L or 6 times L. So this is 12 minus 3 is going to give me 9. Okay, 2 times -3 is -6 plus 8 is going to give me 2, and so on. Okay. So how are we going to show that it doesn't work in the other case? Okay, we'll go ahead and we'll do the same exact thing. We're going to set it up to where we're going to try to write this for -1, 8 is equal to some k times 1, 2, -1 plus some L times 6, 4, 2. Now I just need to solve this system. So I have 4 is equal to k plus 6L. I have -1 is equal to 2k plus 4L. And I also have 8 is equal to -k plus 2L. Okay, and then I just have to try and solve the system. So we'll go ahead and maybe I'll focus on the top and the bottom one first. I'm going to go ahead and add those two together. So taking these two and adding them together, go like this maybe. So 4 plus 8 is going to give me 12. K plus -k goes away. 6L plus 2L is going to give me, so 12 is equal to, what is that, 8L. So L turns out to be equal to 12 eighths, or 6/4 or 3 halves. Okay. Now go ahead and plug it back in to figure out what k is going to be. So maybe I'll plug in the top one. So I have 4 is equal to k plus 6 times L, which is 3 halves. So this cancels to 3. This is 9. Subtract it over. K turns out to be equal to -5. Now, if it spans it, when I plug it back into this middle equation, it should actually work. So plugging back in the values, I have -1 is equal to 2 times k, which is -5, plus 4 times L, which is 3 halves. So I have -1 is equal to -10. This is a 2, so plus 6. Clearly, those are not equal to each other, so it doesn't span it. Okay? Okay, example 4.2.9. So it kind of looks like I goofed up in my notes, and you guys will see this as well. So I have example 4.2.9, which is this. And if you turn it over to example 4.2.10, it's the same exact question. Okay, so we're just going to go ahead and work off of this one. We'll skip the other one. Okay, sorry about that. I guess I didn't catch that in my notes. I'll have to go back and fix that part. Yeah. Okay, so determine whether V1, which is this, V2, and V3 span the vector space R3. So is it possible to make every single vector that's in R3 based off of those three? Okay. So in other words, we have to be able to take some arbitrary vector. So I'm going to create some vector as arbitrary vector B, which I'm going to call B1, B2, and B3. So the goal here is to take and make B, which is going to be equal to K1, V1 plus K2, V2 plus K3, V3. That's what the goal is. Okay, can I do that? Okay, so I'm going to go ahead and plug in all the components here. So I have B1, B2, B3. that is what the vector B is equal to K1 times V1, and V1 is 1, 1, 2, plus some K2 times V2, which is the vector 1, 0, 1, and then plus some K3 times the vector 2, 1, 3. Okay, so now we're going to go ahead and set up the system of equations. So I have B1 is equal to K1 plus K2 plus 2K3. And then I also have the vector B2, which is going to be K1 plus 0 plus 3K3. And the last one is going to be B3, which is the vector K1 plus K2, and then plus 3K3. Okay, I just realized I made a mistake here. This should not be 3K3. This entry right here, this term, came from taking K3 times 1, and that was incorrect, so this should just be K3. Okay? So what this really becomes is this goes back to matrices, okay? Can I solve this system? Or is it possible that the matrix, I'm just going to take the coefficient matrix over here, is it possible that the coefficient matrix has an inverse? So 1, 1, 2, 1, 0, 1, and 1, 1, 3. Okay, is this an invertible matrix? Okay, and if I'll leave you guys a moment to actually figure that out yourself, so pause me for a moment. Okay, and then when you come back, come back. Okay, so I'm going to go ahead and take the determinant here to figure out if it's invertible or not. Maybe the easiest way to do this, I don't know. I guess I'm going to go ahead and pick this this column right here, since it has a 0, and then 2 1s. I'm going to go ahead and work off of this. So in doing so, I have 1 times the matrix. So I'm going to cross off that row and this column. So I have 1, 1, 1, 3. Okay, plus, minus, plus 0, so plus 0. And then minus, plus, minus. So minus 1. Notice I didn't put in the matrix there because it's times 0, so I just left it alone. So 1, so this column goes away, that row goes away, and I have 1, 2, 1, 1. And then in doing so, I'm going to have 3 minus 1, which gives me 2, minus 1 minus 2. So 1 minus 2 is going to give me negative 1. Negative 1 times that gives me plus 1. And I've done something incorrect here. That's because this right here. I made another mistake. You guys didn't catch me. You should have told me. Excuse me. This right here is wrong. See if you can't figure out what I did wrong. So B3 is going to be equal to K1 times 2. So this should be a 2 here, which makes this a 2, which is going to make this a row. So 1, yep, this is a 2 right here. So I'm going to have 3 minus 2, which is going to give me 1, and then minus, so this is the entry. So plus, minus, plus, minus, plus, minus, plus, minus. Yep, so that's right. And then I'm going to cancel this and this. I have 1, 2, 1, 1. I have 1 minus that is going to give me, what am I doing wrong? Oh, that's what I'm doing wrong. You're not catching me. This should be a negative 1. Okay, so it's a minus 1 plus 1, which gives me 0. Sorry about that. That was a struggle. Okay, so what I know then is I know the determinant of this matrix is 0. That means it is invertible. So what does that mean? It means that there is no solution set for this. That means that V1, V2, and V3 do not span R3. Okay, so that's what I know. Okay, last two theorems. The very last theorem is already written out, so there's nothing to go over. Theorem 4.2.4. The solution set of a homogeneous linear equation ax equals 0 and unknowns is a subspace of Rn. Okay, so we're going to go ahead and we're going to prove this. Okay. So the solution set. So I'm going to let W be the solution set for the system AX is equal to 0. Okay. We know that the solution set is not empty. Why? It's trivial, the answer should be, which is literally trivial. When you set x equals 0, the 0 vector, then it's going to equal to 0. So it's non-empty. So W is non-empty. And so all I'm going to do is I'm going to show that it's a subspace, and we have to do this by showing that it's closed under addition and scalar multiplication. So we're going to let x1 and x2 be vectors in W. Now, since the vectors are solutions of AX is equal to 0, then that means I have AX1 has to be equal to 0 and AX2 has to be equal to 0. So it follows then that A of x1 plus x2, once again, I'm taking those two elements, I'm adding them together, and I'm showing that it still belongs in the same system. It's going to be equal to A x1 plus A x2, which is equal to 0 plus 0, which is equal to 0. So that means that it's closed under addition. Okay. So furthermore, I have A times K x1. Okay, I'm going to show that it's closed under scalar multiplication. So I'm taking the k times that vector x1. Well, we know that this is equal to k times a x1, which is equal to k times 0, which is equal to 0. So it's also closed under scalar multiplication. So also closed, and then therefore it's a subspace. So therefore, W is a subspace of R. Okay. And the last theorem, and then we're done with section 4.2. Okay. So if S is the set of vectors v1, v2 all the way up to vr, and S prime is the set of vectors v1, v2 all the way up to vk, so notice that these are not the same. There are non-empty sets of vectors in a vector space V, so they are sets of vectors. Then the span of v1 to vr is equal to the span of v1 up to vk. Let's go over this again. So S is a set of vectors v1 up to vr. Okay. S prime is the set of vectors from v1 up to vk. And these are non-empty sets of vectors in a vector space V, so they belong in there. So this span, these spans will be equal to each other if and only if each vector in S is a linear combination of those in S prime. And each vector in S prime is a linear combination of S. Okay, so it shows us the power of it, that it will span it if they can be written as linear combinations of each other. Okay, and then we are done with section 4.2. All you have to do is go ahead and go back and do the homework, and that will be it for this section. Okay, thanks very much, and I'll see you later. Thanks.